Uh, Good afternoon, everybody. My name is Brahayam Ponton. I'm from the Max Planck Institute of Intelligent Systems. And today I'm going to talk about the effects of measurement uncertainty on the computation of optimal controls. And particularly, I will look at some preliminary results in a contact interaction task. So I work in locomotion, so I will motivate this talk by Just a second, sorry. So in locomotion, there has been a lot of progress in motion planning and optimization of contact sequences, starting from non-convex solvers to custom-made solvers that will exploit the problem structure and render the optimization more efficient. So right now we have real-time solvers for motion planning in locomotion. However, when one tries to execute these motions on a real robot, there are still problems to try to make it. And one of the reasons might be because there's still a lot of information that we don't use in the computation of the control. So the idea that I would like to present today is the use of uncertainty information in order to compute more robust behaviors. And the two types of uncertainty that I would like to show is on the first, it's process noise, that it's an external disturbance, or physical forces that will physically perturb your robot. And on the other hand, we have measurement uncertainty that comes from things that we don't know. It's lack of knowledge, but this does not constitute an actual disturbance to the robot. One example where we see, for example, this discrimination is a Kalman filter. And in a Kalman filter, we have a process model, a measurement model, and we look for a state estimate, which would be sort of a weighted sum between these two models. What is interesting is that in order to compute the Kalman gain, we use uncertainty information, the uncertainty coming from our measurement and process models. And these allow us to optimally weight our trust between our process and measurement models. So for example, the Kalman gain, it's inversely proportional to the variance of the estimation errors. And so if the measurement is noisy, then you will not trust this too much. So the idea is that we would like to transfer this idea of optimally weighting two models to the control problem. Specifically, for example, to a linear control law where you would like to give some trust to the feed forward and other to the feedback, for example, for a contact interaction task. So the approach is as follows. So first, we will try to find a framework that allows us to take into account uncertainty in the computation of the controls. Then we will try to factor in measurement uncertainty by using a Kalman filter. And then we will build an algorithm that does this. So to start, just a reminder of optimal control. In the deterministic case, we usually have a linear system or some system that defines the dynamics of the system. We have an objective. And the AJB equation tells us what the optimal controls are for this system given these conditions. And in this very simple case of linear control, we can get a solution as shown down, which comes from integrating backwards a matrix Riccati equation. Now, what happens when you introduce noise into the system? For example, we have a stochastic optimal control. So noise appears in the dynamics of the system. We look at an expectation of the cost, and the AJB equation is modified. However, the effect is only a diffusion on the cost. It's a linear term on the value function. It's a constant term on the value function, which doesn't enter in the control. So here the certainty equivalence principle holds. Therefore, the control for the deterministic and stochastic case is not the same. It's the same, sorry. This would make sense if the noise were small. However, if the noise is bigger, you would like to probably do something different. And in order to do that, you need to take into account higher order moments. And for example, the way to do it, one way of doing it is by work of Jacobson, where the cost function is exponentiated, which means that now we don't only take into account the expectation of the cost, but also its higher order moments weighted by some coefficient, which makes it either a penalty or a reward. Yes, so now the AJB equation, it's modified accordingly such that the covariance of the noise enters the computation of the control law. And as you can see here, omega being the covariance of the noise, in this case, a process model. So we would have a linear system and a way to compute risk-sensitive controllers. Now, the idea is that we would like to model the distance to the contact as a problem with measurement uncertainty. So besides having a process noise, we would like to have be able to compute controllers that are sensitive to measurement noise. And the way we do it is we extend the definition of the linear system to not only contain the process model, but as you can see in the second line, it's the definition of a state estimate, like how you would get a state estimate from a Kalman filter. And the optimal controls turn out to be function of both noises. So here, we can see that as the process noise increases, the cost that it penalizes, that it generates, increases. So high feedback gains are required to control this. This is not the case in the measurement uncertainty case. So as measurement increases, such as in a Kalman filter, the cost decreases. Therefore, high feedback gains are not required. So this idea leads naturally to try to model a contact interaction task as a problem with measurement uncertainty. And what we do is, it's a simulation experiment where we have a finger and we want to exert a force at the wall. But the distance to the wall is uncertain. We don't really know exactly. So we want to generate a reference force. And if you compute the force with a non-sensitive controller, in the case when there is no uncertainty in the first plot down, both controllers perform similarly. However, as uncertainty starts to appear, it plays a high role in how the forces appear. So the sensitive controller in blue, for example, in the second or third plot, generate higher forces because contact happened before it was expected, and even loses contact. However, a sensitive controller will be able to generate more compliant behaviors and more safer. Just to conclude, so I have shown that there's a difference between process and measurement uncertainty, a fundamental difference because of the cost they penalize and the feedback gains they generate. It might be a good idea to model contact interactions as a problem with measurement uncertainty. Some of the things that are still dirty laundry is that we would need to test these on a more complex scenario, like a higher dimensional system. And also our approximation of the distance to the contact as a Gaussian noise might be inappropriate for more complex geometries. Thank you very much. Any questions?
Thank you. Marin is the first responder.
Thank you. Thank you for the interesting talk and also the interesting example. One thing that wasn't completely clear to me is that why is it necessary to include both the state X as well as the estimate X?
So in a risk-sensitive approach, if you take noise only in the process model, this will generate higher feedback gains. So for example, if you are going to touch a wall and your uncertainty increases because you don't know where the wall is, your feedback gains will increase. For example, imagine you have process noise, which is something perturbing you. In order to keep your hand at some performance, stable, you will increase your feedback gains. So for a contact interaction task, you don't want feedback gains to increase as your noise increases. You actually would like the opposite, right? So measurement uncertainty leads naturally to this behavior, that as noise increases, your feedback gains become smaller.
So, but from a computational point of view, for these type of systems, usually there's a principle called the separation principle.
Yes.
That holds. So certainly the certainty equivalence principle does not hold in the nonlinear case.
Yes, in this case, the certainty equivalence principle does not hold. So the risk-sensitive approach does exactly this, that it is sensitive to the noise, which is not the case when you use the certainty equivalence principle and it's in a stochastic optimal control.
Right, so what I wanted to say is that you essentially, for these type of systems, and especially the cost function that you consider, it satisfies the separation principle as opposed to the certainty equivalence principle. And what this allows you to do is to actually separate the logic for the estimator and for the optimal controller. So one thing that will be useful to look at is the theory on dual control, which has a very, very similar formulation which shows you how to do that.
Yes. So
and it might be possible that it's related or slightly different. I'm not sure, but it will be useful to look at that.
Yes, thank you very much.
Yep.
Yeah, that's true.
Thank you for that great question. Anyone else in the back? No, I think we're getting a little tired. I don't hear. Okay, let's thank our speaker. Thank you.